So good morning and welcome to the 5th class of the 15 lecture series on computer architecture and organization. Last couple of class we have seen about digital fundamentals. We also seen some of the number representations, the signed arithmetic and also the 2's complement arithmetic. Couple of tutorials have been circulated. I hope by this week you will be doing those tutorials, which will further reinforce the concepts that have been covered in those 4 lectures. Today we will go into the next phase of computer architecture and organization, especially the control and the data path. So before we proceed, I would like to cover a little more digital logic, some modules that we will be doing as a part of this control and data path. When we look at traditional computing systems, the computing system could be viewed as 5 layers. I think I mentioned it in one of the earlier classes, but let me just repeat for the sake of completeness. The bottommost layer is the digital hardware. On top of this lies the microprogramming layer, on top of this is the operating system, on top of this is the compiler, and then you have your higher level languages like C, etc. So we have to, if in a computer architecture and organization course, we have to basically address all these 5 layers. What we have done in the first 4 layers, for 4 lectures, was some introduction to the digital hardware and number representation of how data is being represented in the digital hardware. These are something that are fundamental for you to understand how data or programs are actually processed. The next step that we are going to do is to talk about this microprogramming layer, and that is where the notions of control and data path would become much easier. So let us understand what is this microprogramming layer. So let us take a simple C program. Let us say C equal to A plus B. Now let us assume that A and B are available in what you call as general purpose registers. To just explain you what a general purpose register is, the program that you execute is actually in the memory or RAM. And there is an interface between the RAM and the CPU through what we call as a bus. All the instructions and the data necessary for the instructions to execute are initially stored in the RAM. For example, the moment you press C equal to, you write a program, you compile the program C equal to A plus B and start executing it, this entire program is loaded into the RAM. And then the instructions are basically fetched from the RAM. The data for these instructions are also fetched from the RAM, and they are basically executed in the CPU and results are stored back into the RAM. So the instruction in this case is add and the operation and the operands or the data in this case are A comma B, which are called as source data, and there is another data which is C, which is called as destination data. So in general we call it as operands. So this A, B are given some place in the memory, they are stored in the memory. Now they have to be fetched from the memory and executed by the CPU, and the result should be stored back into the memory. So let me write some. So from the memory they are fetched into the CPU, means they are stored in some temporary storage inside the CPU, and this temporary storage is what we call as registers. So a simple program for executing the C equal to A plus B would be as follows. Let us assume C is stored in, say, location 1000 in the memory. A is stored in location, say, 1010. B is stored in, say, location 1020. So the random access memory that we talked of essentially has different locations, and each location has an address like 1000, 1010 like that, and in each address an instruction or a data can be stored. Now let us assume that C is stored in 1000, A is stored in 1010, B is stored in 1020. Now how will this program compile? Now first I will move is an instruction which the hardware will understand and do this. So move into, say, EAX the content of 1000. That means from the random access memory go to the location 1000, get the data and move it to a register called EAX. This register is inside the CPU. So from the memory that is external to the CPU, you are getting the data and storing it in a general purpose register called EAX. The next thing is we move into EBX, sorry, this should be 1010 and this is 1020. I am moving the content of B into register EBX. Now I am adding EAX and EBX. That means the content of EAX will be added to EBX and the answer will be stored in EAX itself. So this is something like EAX is equal to EAX plus EBX. Now what is that answer EAX? That will be now C, because A is moved into EAX, B is moved to EBX, both of them are added and the result is stored back in EAX. So the answer is C. Now I have to move the value of C into 1000. So your single instruction at the C level, which is C equal to A plus B, that is C programming level, when it gets compiled, it just gets translated into 4 assembly instructions. These are called assembly instructions. And who does this translation, or this is a translation. So who does this translation? The compiler does this translation. So what you see in this organization, you see a higher level language, namely C equal to A plus B, and that goes through a compiler, and the compiler gives you this assembly code. This is the language which is called assembly language, that is understandable by the hardware. Your hardware cannot directly understand the C language. It has to get translated by a compiler into another language, namely the assembly language, and it is this language that this hardware can understand. Fine. Now let us take how. So what will the compiler now, what will the hardware now do? It will take instruction by instruction and start executing it one by one. So first it will take move EAX, 1010, it will move EBX, 1020, then it will execute add, then it will execute another move. So the hardware will take one by one and start executing it. Now let us see what it means to execute this. So you write this program C equal to A plus B, you compile it, the compiler will translate into this part. Now when you press your A dot out, or you compile the program and you start executing it, immediately this program will be loaded into the RAM. So let us say 900, 901, 902, 903. These are all addressed in the random access memory. Let us say that move EAX, 1010 be loaded here. Let move EBX, 1020 be loaded here. Add EAX, EBX be loaded here. Then move 1000, EAX be loaded here. Subsequently, let us also assume that in 1000 there is a place reserved for C. In 1010 there is a place reserved for A, and some 1020 there is a place reserved for B. So moment I start executing this program, this whole thing is loaded into the memory as we see here. Can you push it a bit? Okay, so this is how it is loaded. Now, so I'll just erase this part. Now this program has to now execute. So once I load the program into memory, this program has to execute. So what it means by executing? First and foremost, we should understand that there is a hardware called program counter. The program counter points to the next instruction to be executed. So initially when the program is to execute, the program counter will now point to 900. So what will the hardware do? It will fetch the instruction from 900. From address pointed by program counter. So the first step is this hardware will now fetch the instruction from address pointed by program counter. That means it will fetch this instruction, namely move EAX, 1010. This will be fetched from the memory, random access memory, into the CPU. Then the moment it fetches, as I told you, this program counter always points to the next instruction to be executed. So now your program counter will be incremented. Now initially program counter was pointing to 900 and the instruction in 900, namely move EAX, 1010, has been moved into the CPU. Now your program counter will now point to 901. Now after this is fetched, the hardware should know what should it do. Already you see there are 4 types of instructions here. One is move, another is add, now we can have multiply, we can have several things. So first and foremost, the hardware should know what that instruction has to do. So the second step would be to decode that instruction. So what it means by decoding the instruction, at the end of this stage, hardware will now know, yes, it has to move a data from 1010 to EAX. At some point of time, the hardware will know when it is executing, I have to add the data that is there in EAX and EBX. Correct? So after the decoding of the instruction, the hardware will know what exactly it has to do. The next step would be to, now it has to do something, it has to fetch the data from 1010 and store it in EAX. In the case of add EAX, EBX, it has to fetch the data from EAX and EBX, those are registers, add them. So first it has to fetch the data. So basically the hardware, the CPU will have something called the ALU, arithmetic logic unit. So to the arithmetic logic unit, I should provide these 2 data, namely EAX and EBX, so that it will add. So the next step is to fetch the data necessary for executing the instruction. So first I will fetch the instruction, next I will decode the instruction, now I will fetch the data that is necessary for executing the instruction. Now the fourth step would be to actually execute the instruction. And the fifth step would be store the results. So, and then again this will go back to step 1. So, go to step 1 till program completes execution. So, we start with 900, we fetch the instruction, namely move EAX 1010, we decode the instruction. Once we decode the instruction, then we fetch the data necessary for executing the instruction, namely we fetch 1010. In the case of executing the instruction, we just pass it without any change to the register unit, and in the storing the result, the whatever we have passed is stored into EX. Similarly, in the case of 1020, moving 1020 to EBX. In the third cycle, your program counter would be pointing to 902, where you get add EAX.EBX. You decode the instruction, you know it is add. Then you fetch the data EAX and EBX, add them in the ALU, and then store back the result in EAX. Then you go back to 903 and so on. Right? And this goes on till the program gets finished. So let the 904 instruction be something like halt. Let it stop. So essentially executing an instruction comprises 5 steps. I will give a small codification for the step or abbreviation for the step: instruction fetch, instruction decode, data fetch, execute, write back result. Okay. So the instruction fetch, instruction decode, data fetch, execute and write back. These are 5 stages in the execution of any instruction. Chat. Okay. Fine. Now, with this level of understanding, let us say I had a C program, the compiler compiled it into this program. When I execute this program is loaded into this memory, and this is how these instructions are executed one by one. Now, we will now go and introduce what a micro architecture or a micro programming is from what we have understood so far. So let us take, I am just erasing this part. If you want, you can copy, I will give you a minute time. IF, ID, DF, EX, WB. We will be using this quite frequently. Please remember this abbreviations. So these are 5 steps in the execution of an instruction. I am erasing this. Now, when I said add EAX, EBX, this itself comprises of 3 to 4 instructions. For example, after the instruction add EAX, EBX is decoded, now I have to fetch EAX to ALU. I have to fetch EBX also to ALU. I have to tell ALU add them. Then I have to store result in ECX, in EAX. This is what I mean by add EAX, EBX. Fetch EAX means fetch the data in EAX to ALU, or essentially move the data that is stored in the register EAX to the ALU, move the data that is stored in the EBX into the ALU, then tell the ALU add, then the result again I have to move back it to EAX. So just add EAX comma EBX comprises 4 small instructions. These are basically called as micro instructions. This is an assembly language, this is a machine instruction. To execute this machine instruction, the machine further breaks it into other small set of instructions, and those smaller are still what do you call micro instructions. They are called micro instructions because they are below the assembly instruction. So for every such instruction, the assembly instructions that you see, a small set of actions would be carried out by the ALU to basically execute that assembly instruction, and this is basically called, those instructions as we are seeing are called micro instructions. The question? Okay. So now what we need to understand at the micro programming level or the micro architecture level is how these micro instructions are basically executed, right. So let us go and in the next this class and the remaining part of this class and in the next class, I will basically cover how a given assembly instruction, namely say add EAX comma EBX, is executed, rather how these 4 micro instructions corresponding to this add EAX comma EBX is executed. So what would be the hardware necessary for it to execute, how is that hardware organized, is what we will cover in the next 1.5 class, remaining part of this class and the subsequent lecture. Okay. So I will erase all these things and we will now just take add EAX and this set of 4 instructions. So as we have seen, there are 2 translations that exist. The first translation is the C program got converted, that C equal to A plus B essentially got converted, one of this instruction was this add EAX EBX. So your C program got converted into an assembly code. Now this assembly code essentially gets converted into a set of micro instructions. The first translation was done by a compiler, the second translation is done by your micro architecture. Now what is the difference between the first translation and the second translation? In the first translation, the entire program, say I had main, the entire program was compiled and converted into an assembly code. I can say that the entire program as a whole was translated to the assembly code. I am writing these things on the board because I am giving time for you to copy. I hope all of you have a notebook and a writing pen and you will copy this. Okay. So the entire program as a whole was translated to the assembly code. This translation is basically called as compilation. And the software that converts this language, the entire program into assembly code is called a compiler. I don't know about individual universities, but typically the compiler course is a very important course in the CSC curriculum, and mainly you may read it in your 5th or the 6th semester. You will be reading compilers, but compiler is a very important course. If your university syllabus does not have compiler, please go and look at some of our NPTEL lectures on compilers, and of course there are also some other courseware available, but please do learn compiler. And there is a GATE examination. The GATE examination syllabus has some part of compilers in the syllabus. Please at least go through that and study compilers. Compiler knowledge is very necessary for a computer science and engineering student. Coming back, so the translation of the entire program as a whole to the assembly code is called compilation. Now what happens? Each instruction in this assembly code is taken one by one and executed by the hardware. So there is another translation wherein each assembly code is translated into the microprogramming instructions, but this translation is different from this translation. The main difference is here the entire program is compiled, translated, and then it is executed, but here every instruction of the program is taken, it is translated and immediately executed, then we take the next instruction, again you translate and execute. So there is a subtle difference between this translation and this translation of converting assembly code to micro instructions. And this happens wherein every assembly code instruction is taken, converted to micro instruction, immediately they execute, then take the next assembly code. So one by one the instructions are taken and translated on the fly, and then they are executed. This type of a translation is called as interpretation. In olden systems, say 20 years before, they will be called as interpreters. The old basic programs, they basically get interpreted. What I mean by interpretation is that every instruction of that basic program will be taken and executed, then the next instruction. Now we have compilers which take the entire program and compile to assembly code, but then the hardware takes each instruction of the assembly code, convert it to micro instruction, immediately execute, and then go and translate the assembly code. So the whole assembly code is not translated to micro instruction and executed, rather every instruction is taken and then the corresponding assembly code is generated. Every assembly code is taken and the corresponding micro instructions are generated, they are executed, and then you go to the next assembly. So please understand that there are two translations involved. The first is the C program getting converted to assembly code, and then the assembly code getting converted to micro instruction. The first translation is called compilation, and it is done by a compiler, and the second translation is interpretation, and it is done by the microarchitecture or the hardware. I hope I have made this very clear. Right. Now what we will be studying is this interpretation, how this instruction gets translated into this micro instruction. As we have limited interaction, I am repeating every statement twice or thrice, so that if somebody did not understand, then there is a good chance that you all understand. By 3 times, I hope by any random phenomena, the expectation can be 1. So I'll be slightly repetitive because I have very limited interaction. There are around 30 institutions here, and since I am not on I don't see the face, I see space of 1 or 2 here. So I don't know whether you followed or not. So I am repeating it. So kindly bear with me. If you understand the first time, well and good, it's a revision. If you don't understand the first time, then you will thank me for repeating it again. Okay. So before we proceed into this interpretation, I would like to introduce today, before we wind up in the next 5 minutes, a set of hardware that would be useful. All of you know what a multiplexer is. It is given by this diagram. If your select is 0, if select is 0, out A, else out is B. Okay. So this is a 1 bit 2 to 1 mux. A and B are 1 bit and this is a 2 to 1 mux. Right. Suppose I want this to be K, say let us say 2 bits, each one to be 2 bits. How will I realize it? It's a very simple thing. I put, let me call that A and B as A1 B1 and A2 B2. This is out 1 out 2 and I give the same select input to both. So if select is 0, your out is A, but both out and A are 2 bit numbers, else out is. So if your A and B are 2 bit numbers and out is also a 2 bit number, then using the select I can put several such mux together, and 2 such mux I have put now to basically route A1 A2 to out 1 out 2 or B1 B2 to out 1 out. So this is called a 2 bit 2 to 1 mux. So I have a choice between 2 entities, namely A and B, and I want to decide whether I want A or B using the select bit. Then I use, and each of A and B are say 2 bits now, so I use 2 2 to 1 mux. So this 2, please understand, is decided by how many choices I have. In this case I have 2 choices. This 2 is decided by, or this 1 or this 2 is decided by the size of the choice. This is number of choice. Are you all following? This stands for number of choices. I have 2 of them here. This stands for size of the choice. If I had just each choice is only 1 bit, then I put 1 mux. If I have 2 bits, then I put. Suppose A and B are 3 bits and out is also 3 bits, then essentially I will put one more thing here. I call it A3 B3 and this will become out 3 and your select bit goes. So this is a 3 bit 2 to 1 mux. Like that I can go for 16 bits or 32 bits, etc. You all follow this? Now let me just say, if select equal to 0, out equal to A, if select equal to 1, out equal to B, if select equal to 2, out equal to C, if select equal to 3, out equal to D. Now what are the number of choices? There are 4 choices between A, B, C and D. So, and let me assume to start with each is a 1 bit number. So I need a 1 bit 4 to 1 mux. So how will it look like? 0, 1, 2, 3, and I have 2 select 1 and select 2, and I have given A, B, C, D, and this is out. If select 1, select 2 is 0, 0, then I get A. If it is 0, 1, I get B. If it is 1, 0, I get C. If it is 1, 1, I get D. Corresponding decimal values are 0, 1, 2, 3. Now, if each of these A's and outs are going to be, say, 2 bits, then I will call this as A1, B1, C1, D1, out 1. I will have another mux which again has A2, B2, C2, D2, and I call it out 2, and the same select will go to both. Now I can expand it up to say 16 bits or 22 bits or 32 bits or whatever. So essentially I am introducing a concept called bus multiplexer, which can be a k bit R to 1 mux, where this k stands for the bus width and R stands for the number of choices. R stands for the number of choices, while K stands for what I call as the bus width. What is a bus? Bus is nothing but a collection of lines that carry data from one part of the chip to another part. So most of your colleges will have buses, right? What will the bus do? It will take you from one point and drop you at another point. Similarly, a bus in a architecture will take data from one point and drop it in another point. So now here also what it is doing from from the bus I really want to select one of those buses. So if I have a k bit bus, meaning k data has to move from one point to another, there will be several such k data and I have to select one of those k data, then I use this k bit R to 1 mux, where k is the bus width or the size of the choices and R is the number of choices. Okay. So this is, so please keep this in mind in the next lecture, that is on Wednesday. I will now use this bus multiplexer to design the microarchitecture. One thing I don't want you to forget is that in the next lecture we will again be doing what we call as the micro instruction execution. Please remember, add EAX, EBX, and also the set of 4 micro instructions. One thing is to fetch EAX to ALU, fetch EBX to ALU, tell the ALU to add, store back the result back into the one of the registers. So that particular machine instruction had 4 micro instructions, and what we will be covering is that how that assembly instruction, namely add EAX, EBX, is translated into these set of 4 micro instructions, and these 4 micro instructions how they are going to execute. So this is precisely what we will be covering in the next class. Okay. So with this I am opening up for questions. What is it? Please use hand raise button at the left side. Okay. So I am just opening up for questions. So if you have questions, please hand raise fast. The next class is scheduled in another 10 minutes. So I like to answer as many questions as possible. Subjects are well learned by questioning, not by listening. And your questions also give me a pointer of how much I have communicated. So it's a good feedback for a teacher. So please do ask questions. I don't know what feedback to take today. Are all my explanations very clear that nobody has any questions? I don't think so. Yeah, question. The PC changes, when does PC change its value? The PC change its value immediately after an instruction is fetched. For example, if you remember, there was an instruction stored at 900. The moment it is fetched from 900 into the CPU, immediately your PC advances to 901. So there were 5 stages: the instruction fetch stage, the instruction decode stage. In the instruction fetch stage itself, the PC changes its value. Is it okay? RVCE teacher, is it okay? Please type on the chat, okay or not okay. Yes sir, okay, good. Next. Yes. Yeah, please ask your question. Yes, please ask. Yes, good morning.
So when we are adding EAX and EBX, the result is stored in EAX register only.
Yeah. So that is how you design your instruction set, right? I am using, see, I have 2 operands, I want to add it. So there are 2 ways by which you can store. I can say add ECX, EAX, EBX. Wherein I take the values from EAX and EBX and store it in ECX. This is called a 3 operand instruction, because there are 3 operands here. What happens is, by doing such a thing, the size of your instruction becomes fat, big, and there is no necessity for you to use another register because you may not need EAX anymore. So many of the architecture, especially the Intel machines that you execute, they don't support 3 operand instructions, but instead they support only 2 operand instructions, because then it becomes easy for them to manage. So that is why this is gone, and I say add EAX, EBX, where you take EAX and EBX as input, get the answer and then store it back in EAX. It's something like C equal to C plus D in C, right? Something like that is what is happening here. And the reason why we do it is because 3 operand instructions become more complex for you to decode. A 2 operand instruction is much easier for you to decode. When we look at the microarchitecture, if it is a 3 operand instruction, what it means to do will be much different than what we are going to do for a 2 operand instruction. So that is one of the reason why the micro architects who design this micro architecture decide on how many operands should I have in a particular instruction. And many architectures, the Intel architecture that is quite common, that many of you will study as a part of your assembly language lab, etc. The Intel architecture actually supports 2 operands. But there are other architectures. So how many people there in that college? All of you are very smart, right? With coat and tie, you all look very smart here. Okay, smile, man. It does not reach you. Only one of you smile. All of you smile. Can you smile? Please, the guy who put the question, please smile. Okay. So, so much latency, right? Okay. So that is one of the reasons why many of all of you. How many people have mobile phones? Can you put your hands up? How many of you have mobile phones there? Okay. So there is what is the processor inside the mobile phone? Do you know? It is called an ARM processor. Many of your mobile phone has ARM processor. That ARM processor supports 3 operand instructions. So whatever is very close to your heart and hand has 3 operand instructions. But whatever you see on your desktop or machine, the Intel machines that you see, they are 2 operand instructions. Okay. So when we actually cover some part of instruction set architecture, I will tell you more about pros and cons of having 3 operand versus 2 operand instruction. But an immediate answer to your question is, when I keep increasing the number of operands, the decoding becomes more complex, and that is why some of the architectures restrict themselves to operand instruction. Is it clear?
Yes, sir.
Right. Yes. Okay. Next.
Good morning.
Good morning.
Good morning, sir.
Yes. Good morning.
I want to ask a question that if I have a follow in C program,
Huh?
if I have a for loop in C program, it is to be executed, and how is it converted into assembly language?
Oh, it's very garbled here. Can you type on the question window? Please also type on the question window. Don't cut your video, but please type on your question window also. RV80 teacher wishes me a Valentine's Day. Yes, I am a little old for it. But anyway, thank you. And so what is the size of a program counter? The program counter size would be equal to the size of the memory that you are wishing to address. For example, the Intel architecture is a 32-bit architecture, so they will look at 32-bit for addressing memory, and so it will be 2 power 32. 2 power 32 a combination, so the size of the program register would be 32 bits. How to execute a for loop is the question from JISCE. Yes. How to execute a for loop? There will be something called branch instructions. I will be covering it when I go into the pipeline architecture, which would be 7th or 8th lecture. I will be covering that there is something called branch instruction, and you use branch instructions to compile a C program which has a for loop to the corresponding assembly code. Any role of control unit for executing a for loop? Of course, there is a very major role of control unit. The control unit is responsible for executing any instruction, whether it is branch or whether it is add or anything. So the control unit sort of is the brain of your CPU. Internally, it's again the module which basically governs the entire CPU. So the control unit has a major role to play in the execution of any instruction, and so is the case of a branch instruction. Next question. Recap, please.
Good morning, sir.
Please be, good morning, please be loud. You had your breakfast?
Yes, sir.
I did not have, still I am loud, no? So you should be much louder than me. Yes, what did you have for breakfast?
Idli, sir.
Ah, very good. Excellent dish. Yeah, tell me.
What is the difference between a microcode and a machine code?
Ah, that is what I have been talking now. Add EAX, EBX is a machine code. Now that add EAX, EBX is getting translated into 4 small instructions. Each one will be a microcode. So what is that microcode? Next class I will explain you in detail. But what you should understand in today's class is that assembly code add EAX, EBX, which is the machine code, as far as we are concerned, that is what we see, is internally inside the chip getting translated into small 4 other smaller instructions. What are those instructions? How will they be looking like? All those things I will be covering in the next class. But now today understand that it is not just executed as it is further converted into 4 smaller instructions, and each of those instructions is called a micro instruction. Am I clear?
Okay, sir. Yes, sir.
Yes. Thanks.
Thank you, sir.
Yeah. Yeah. Next. Yes. Yes.
Sir,
Can you come in front of camera?
sir, question is already, you answered our question already, the role of control unit.
Yes, okay. Okay. Yes, okay. Okay. Do you have any other question?
Thank you, sir.
Thank you. Okay. Okay. Question. What is it? That they have to, I have answered already. Okay. That's it from users, anybody? So any more questions? If there are no more questions, okay, thank you, and we will meet next Wednesday. Okay, so all it is valid, it's a very happy Valentine's Day. Thanks.